over the last couple of days, we've differentiated between two kinds of energy. Energy, remember, the ability to do work. Not necessarily doing work right now, but the ability to do work. The two types that we differentiated were kinetic energy and potential energy. Can anybody tell me what the difference is between those two types of energy? Yep, Aiden?
Kinetic is like moving.
Good. Kinetic energy is energy of motion. So if something's moving, whether it be me walking across the room here, or whether it be my pen as I'm writing on the board, or whether it be literally tiny little molecules vibrating around producing heat, which there's not a lot of in this room right now, we've got kinetic energy. Anything that's moving has kinetic energy. Yep. Okay, kinetic energy is absolutely dependent upon speed. Okay, it's dependent upon two things, mass and speed. What's it more dependent upon, mass or speed? Speed, because it's v squared, right? It's EK is equal to 1/2 mv squared. Depends upon mass and speed, but more on speed than it does on mass. But be careful with your second thing that you just said. Potential energy is dependent upon height. Potential energy is not necessarily dependent upon height. There's lots of different kinds of potential energy, right? Potential energy is stored energy. It's not doing anything right now. It has the ability to become kinetic energy. It has the ability to start moving at some point. But there's different kinds. There's different things that can result in things moving. Okay, we talked about one yesterday, which was gravitational potential energy, right? That's energy that's dependent upon height. Stored energy, energy that's not doing anything right now, but can cause something to move later on. That's due to a height. But there's other kinds of potential energy as well, right? Go ahead. Yeah, go ahead. Yeah. Absolutely. Good question. If kinetic energy can turn into potential, then can potential energy turn back? Sorry. What did you say? If potential can change into kinetic, then can kinetic change back to potential? And the answer is absolutely it can. Okay. In the end, the simplest example of that might be a car going up a hill. Okay, if you've got a bicycle going up a hill, you're pedaling as hard as you can, but then you don't feel like pedaling up the hill, so you just let it's the inertia of the bike do its thing, right, and try to coast up to the top of the hill. Well, what happens is you go up that hill. You're pedaling really, really fast. You're going at 30 kilometers per hour. You stop pedaling. You coast part way up the hill, right? As you're coasting part way up the hill, you're slowing down. So kinetic energy is decreasing, right? But you're going up the hill. So what's increasing? Gravitational potential energy in that case, right? So as you go up the hill, you're slowing down, but you still have the potential to go back down the hill and gain that speed back again. So in that case, you're converting absolutely kinetic to potential energy. Does that make sense? There's other examples of that as well, right? Obviously, other examples of it as well. Sometimes kinetic energy in something you do, okay, increases muscle mass and increases potential energy, ends up increasing potential energy in your body, okay, chemical potential energy. In the end, there's almost always a way of converting potential to kinetic and kinetic to potential. It's just easiest to look at it in terms of gravity there. But okay. So kinetic energy we said was 1/2 mv squared, and potential energy, gravitational potential energy that is, was mgh. Is kinetic energy a vector or a scalar? How about potential energy, a vector or a scalar? They're both the same, right? They're both going to be what? Scalars. There's no direction associated with energy ever. What does V stand for right there? Tony? Speed, and it's going to be measured in meters per second. Good. What is G there? Yep. Okay, so what's its value? Negative 9.81 or 9.81? Just 9.81. Potential energy is a scalar. We're just going to drop the sign of that negative, drop the sign of that 9.81 when we plug it in there. What does H stand for? Stephanie? Yeah. No, not in the context of energy. Doesn't matter whether you're dropping a ball or whether the object is sitting at the top of the hill or whatever, g, we're just going to make positive 9.81 there, always. Okay. When you're dealing with it in terms of a force or something like that, okay, like we have up until this point, then keep making it negative. Keep doing what you've been doing. Don't change anything that you've already done. But for these problems involving energy, we're going to make it positive always. What's h stand for? Who's? Height. But we got to be careful with that, right? The height is always measured relative to something. What's the height of Ryan's pencil right now relative to the desk? Ryan, what's the height of your pencil relative to your desk? Where is your pencil right now relative to your desk? Okay, so what's the height relative to the desk? Right. The height relative to the desk is 0. But the height relative to the ground below it isn't 0. It's more like a meter. So it's got potential energy relative to the ground because it has the ability to fall to the ground. But it doesn't have potential energy relative to the desk because it doesn't have a height relative to the desk. It's on the desk. It's not going to fall to the desk when it's already on the desk. Potential energy is always measured relative to something, but you can make that something anything you want. Usually, it's the ground. But we can make it something else if we wish, like our hand or like the top of the desk or whatever. All right, we also talked about one more kind of potential energy, which we'll do in more detail today. So I'm not going to really address that right now, other than to tell you what kind it was. Remember, we talked about spring or elastic potential energy was the energy that was stored in a stretched or compressed, squished, right, spring or elastic. You guys know that when you pull an elastic, let it go, okay, it fires off. It becomes kinetic energy. Well, that kinetic had to come from somewhere. It came from the stretched elastic. And we're not going to even write down the equation right now because, again, after we check over our homework, we'll focus on that. All right. Your homework last night was page 298, questions number 1 to 3. All right, so we got 298, 1 to 3. Any issues with any of those 3 questions? My guess is number 3. Okay, any others besides number 3? That's it? All right, number 3 it is then. It says a winch pulls a 250 kilogram block up a 20 meter long inclined plane that's tilted at 35 degrees to the horizontal. What's the change in gravitational potential energy of this block? The question is at its heart not a very difficult question. What's the change in potential energy? Well, it's final minus initial. If you can get the final energy by saying mgh, and you can get the initial energy, which is just 0, then we just subtract the 2. The problem is finding the final potential energy, mgh, because we don't know what the height is. So we've got to get that height. Draw it out. Maybe that'll help. We got a 35-degree angle here. We got a 20-meter long hill right here, and we want to find the height. Any suggestions that you might have that we can use to find that height? Seth, what did you do to find the height there? Yeah. Jordan, what did you do to find the height? Cosine 30 degrees is equal to height over 20? Okay, almost. Okay, cosine gives us which side of this triangle? Gives us the bottom side, the adjacent side, right? Now, that's correct. There's nothing wrong with doing cosine 30. The only thing is you got to recognize that you found something that is correct, but not what you're looking for. We're looking for the y component here. If you want to do the x as well, go ahead. We only need to do the y component, so therefore we're going to use sine. Sine is opposite over hypotenuse. 20 times sine 35 gives me, does anybody have the value for that? Jacob? 4715? Okay, thank you. So 11.4715 meters. Good. Now it's an easy question. Now that we've got the height, all we have to do in order to find a change of potential energy is say it's the final potential energy minus the initial. But the initial is just 0, right? Because it starts at the bottom level. So the mass here, what was the mass? It was 250 kilograms times the gravity, which is positive 9.81 here, times the height, which is 11.4715. Jacob, when you use the unrounded number there, did it work out for you? Okay. Just a word of caution, guys. We all do this at some point. We round somewhere where we shouldn't round. Okay. We look at this and say, geez, it should be 3 digits, right? 3 digits, 250, 20.0, 35.0 should be 3 digits. That doesn't mean you should round your height to 3 digits or to 2 digits or whatever. Unless it's a final answer, let's keep all the numbers to as many decimal places as you can. 3, 4, 5 decimal places. You don't round it to 11. Don't even round it to 11.5. Go 11.4715, multiply those together, and when we do that, that should give us 2.81 times 10 to the 4. Is that good? Is that okay? All right, so kinetic energy, not too bad. Probably the hardest thing with kinetic energy is rearranging the equation to solve for V, right? Because you got a V squared in there. Not a huge deal with that, though. Potential energy, not crazy either. That was probably our hardest question where we had to find the height by using some trigonometry. People don't seem to like trigonometry. I don't know why. Spring or elastic potential energy, that's our last kind of energy that we're going to deal with in Physics 20. It's the energy that's stored. That's a big word, right? Stored. If you see that word stored, we mean potential energy of some kind or another. It's the energy that's stored in a stretched or compressed, like a squished spring or an elastic or something that's like a spring or an elastic. Okay, 3 weeks from yesterday, you're going to go to West Edmonton Mall and complete a number of assignments based on the amusement park rides there. One of those assignments is going to be based on the bumper cars. The bumper cars have rubber bumpers. Remember what I'm saying here right now, okay? The bumper cars have rubber bumpers. Now, why do they have rubber bumpers as opposed to steel bumpers? That's one of the questions on your assignment for that. Why do they have rubber bumpers as opposed to, say, steel bumpers? Okay, so steel against steel would cause you to crash and it would hurt. Let's expand on that a little bit, though, Carrie. So the rubber creates the objects to bounce off of each other? Kinda. Let's get a little bit more physics-y, though, on that. Yeah? Okay, so it helps to absorb the impact. What's the impact that we're worried about here? What is it that if you're involved in a collision is going to end up ultimately causing the force to hurt you? Yep. Okay. Okay, your head staying in one place or your head continuing to move depending upon how the collision takes place. I'm looking at kind of at a different angle here, though. When you're driving down the road at a really, really slow speed, you have just a little bit of what? Versus when you're traveling down the road at a high speed, you have a lot of that something. Not what I'm looking for there. Yes, momentum, but we're looking for another term because you haven't learned momentum yet. Yeah. Kinetic energy, there we go. Phew, I didn't think we'd ever get to it. We have a little bit of kinetic energy versus a lot of kinetic energy. When two bumper cars collide, what does the rubber bumper do that the steel doesn't do? It compresses, right? So what does that do? It converts the kinetic energy into potential energy, into elastic potential energy. So you don't get hurt because you're not absorbing the kinetic energy. The bumpers are absorbing the kinetic energy and converting it to elastic potential. Now, the other upside to that, obviously the biggest upside, is that you don't get hurt when the collision takes place because the kinetic energy is absorbed by something other than you. The other upside to it is what happens when that bumper starts going back to its regular shape, when it's not compressed anymore. Well, the potential energy in that case gets converted back to kinetic energy, which causes the car to go backwards. Right? Does that make sense? So we talk about elastic potential energy as the energy that's stored in a spring or an elastic that's compressed or stretched, but it can be something else as well, like rubber on a bumper car. Right? Anything that acts like an elastic or a spring contains spring or elastic potential energy. Does that make sense? Okay, does everybody remember the answer to that bumper car question? Because that is the last question that you have on your West Ed assignment booklet. Okay, why do we have rubber bumpers as opposed to steel bumpers? Okay, and the answer I just gave you, right? In the end, it's because the rubber bumpers absorbed the kinetic energy of the bumper car and converted it to elastic potential, which means that you don't have to absorb the kinetic energy and get hurt. Now, I showed you an equation a couple of days ago and yesterday during our review for elastic potential energy, but we didn't explain that equation. Today we're going to do that. Potential energy, always given by the same symbol, whether you're talking about elastic potential or spring potential or gravitational potential, it's just E subscript P. If it was gravitational potential, it would be mgh. If it's elastic potential, it's 1/2 kx squared. Now, what do these variables stand for? Okay, EP, that's the easy one, right? Elastic potential energy. And the units are going to be, of course, joules. It's a scalar, just like any other kind of energy. X stands for displacement. But I want you to be really careful with this one, because there's two different kinds of displacements. It's in meters, by the way. Two different kinds of displacements. Here's the first kind of displacement, the kind of displacement that you're used to having, that you're used to using. Okay, have a look at this hair elastic, this hair, what do you call it, like a hairband, whatever. Okay, this elastic that I have in my hand. Here's the first kind of displacement that you've used up until today. The movement of the elastic, right? The change in position of the elastic. That displacement is delta D displacement, not X. Okay, the X displacement here that we're looking for here, if I can find that elastic now after I threw it. There it is. The X displacement is not how far the elastic has moved. It's not how far the bumper car moved during the time that it was involved in the collision. Put it away, please. This X displacement is how much it stretched or squished. So it still involves movement. Right? It still involves a change in position, but not the same change in position that you're used to using. It's not how far it's gone, it's how far it's stretched or how far it's compressed. So I'm going to write that down off to the side here, because I don't want you to get that mixed up. We'll say how far the elastic, but remember when I say elastic, I use that term interchangeably with a spring, because the same thing applies for a spring or the rubber bumper cars or whatever. How far the elastic is stretched or compressed. What do you think K stands for? You're not going to be able to tell me exactly what it stands for, but just kind of, what does it mean? A coefficient of a spring. Okay, I like that. That's not the actual term for it, but you're kind of right. Yeah, you're kind of right. What were you going to say, Jake? Kinetic energy? Nope, but that's a good guess. Bart? Okay. I like the coefficient of spring. What we actually call it is a spring constant, but it amounts to pretty much what you're talking about there, right? A spring constant is just a measure of the spring, how stiff the spring is, or the elastic is, right? The spring on your car, right, that holds your car up, right, that surrounds the shocks on your car, has a really, really high spring constant. Okay, it's really, really stiff. It's really, really difficult to compress or stretch that spring. But the spring that's in your pen, when you take your pen apart, has a really low spring constant. It's really easy to compress that. The higher the spring constant, the more energy the spring will hold. But the more difficult it is to compress it. So it's kind of a trade-off there. What do you think is more important in terms of potential energy? What do you think affects the elastic potential energy more? The spring constant or the amount that it's stretched? The amount that it's stretched, yeah. When I was telling you the story about our little clothespin guns, again, we didn't know anything about spring potential or elastic potential energy, or kinetic energy, at least in a scientific way. But still, we knew at some level that it didn't really matter what elastic it did matter what elastic you used. It did. But more important than the type of elastic you used was how far you stretched it. Okay, at some level we knew the more you stretched it, that was better than having a better elastic. Okay, if it was a trade-off between a good elastic and being able to stretch it far, then we wanted to stretch it far because we knew that would make it go faster. Why does that matter more? Because it's x squared. It's not k squared. It's x squared. Units for spring constant are newtons/meters, newtons per meter. Every spring has its own unique spring constant. It's different. The higher it is, the more stiff it is, the more potential energy it will hold, but the harder it is to stretch. Now, there's one more little thing that I have to teach you in order to use this equation sometimes. It's called Hooke's law. We'll talk more about Hooke's law in our last unit, but we'll introduce it here today. Hooke's law provides for us the relationship between the displacement of the spring or elastic, not how far it's moved, right? It's like taking Carrie's hair elastic and throwing it across the room. That's not the displacement I'm talking about, but rather the amount of stretching or compressing. Okay, X provides for us the relationship between X and force. Now, this is a different kind of relationship because for the first time, force is not constant. The force depends on how much it's stretched. You guys know that, right? And again, when I was 8 years old and making clothespin guns, I might not have known about Hooke's law or elastic potential energy, but I knew that the more I stretched the elastic, the bigger the force was required to do that, right? The bigger X is, the bigger F is. The force that you pull on that elastic with gets bigger as X gets bigger. It becomes harder to pull, harder to stretch the more you stretch it, or harder to compress the more you compress it. Now, the reason that we introduce Hooke's law here, F is equal to K times X, is because many times we're doing a question involving elastic potential energy, we don't know the value of K. We have to use this equation for Hooke's law to find the value of K. If it takes this much force to stretch it this far, then let's get the spring constant, and then let's plug the spring constant back into the potential energy equation. Okay, not always. Sometimes you're given K, but lots of times you're not. Lots of times you got to find it and then plug it back into there. What value would F be measured in there? Or what units, I should say? Newtons. And the value of X is displacement again. Remember, not the movement of the spring or the elastic, but rather the amount that it's stretched or compressed, and that's going to be meters. That's where the units for spring constant come from, right? Newtons over meters, newtons per meter. All right, here's our first problem with elastic potential energy or spring potential energy. 6.4 on 301. Says the spring is stretched to a position 35 centimeters from its equilibrium position. Equilibrium just means like a natural balanced position. Before the elastic is stretched or compressed, just sitting there on the desk, that's its equilibrium position. So that means that X, the amount that it's stretched or compressed, the displacement, is going to be 35 centimeters or 0.350 meters. The force exerted on that spring is going to be 10.5 newtons. I'm going to put absolute value signs around there, actually indicating that it's the magnitude of the force. Okay, so we're not showing, we don't have a direction, just the magnitude of the force. If you leave the absolute value signs off, we're not going to lose any sleep over that. We want to find the potential energy. And then, you know what, let's deal with B later on. Let's do one thing at a time here. We're dealing with elastic potential energy, not gravitational potential. So it's going to be 1/2 kx squared. We have x, but we don't have k. How am I going to find k? How am I going to find k? Yep. The absolute value means that there is a direction, because it's a vector, but we don't know what it is. Okay, so a lot of times you're just going to forget to put that around there. A lot of times I forget to put the absolute value sign around there. So it's not something that we're going to lose any sleep over at all. Okay, but strictly speaking, in this case, okay, we don't know what direction that force is. So strictly speaking, it should be an absolute value. Okay. Was someone going to find K? Right. That's Hooke's law, right? Hooke's law. K is equal to F over X. The force here is 10.5 newtons. The X is 0.350 meters. And we calculate the value of K in newtons per meter. We do that, we end up getting 30. What would the units be for this? Newtons per meter. So now we can turn around and plug that into my potential energy equation. EP is equal to 1/2 times 30 times 0.350 squared. Let's figure out what that is now. We end up getting 1.8375 joules. We're going to round that to 3 digits, so it's going to be 1.84 joules. Now, the reason I wrote down my unrounded number there is in case I need that for question B. I'm not sure if I'm going to get or not. Just in case I do, I want to have the unrounded number. Is that good? Not crazy hard, eh? What about question B now? B says, if the stretch in the spring is allowed to reduce to 20 centimeters, what's the change in elastic potential energy? So really what we're looking for here is delta EP. It's the final potential minus the initial potential. And we already have this value. We already have the initial potential. Okay, it was 1.84 joules. So let's get the final potential here. And then subtract the two. The final potential is 1/2 kx squared. How do we find k? How do you find k here? Lewis? F over x. Okay, so let's go. K is equal to F over x. So what do we got now? The force is 10.5 newtons. Hold on before you write this down, okay, guys? Don't write this down yet. Force is 10.5 newtons. Whoops, this should be x, right? X is 0.2 meters, right? That's wrong. Okay, what's wrong with what I've just done? Who can find the mistake, Gary? No, it doesn't say the differences. It's reduced to 20 centimeters. So the displacement was 0.35. The displacement is now 20, or 0.20 meters. So that's not our issue. Yep. Why 10.5 over 15? Because it's a difference. Okay, good guess, but no. Yeah, the force isn't 10.5 anymore. The force is 10.5 when it was 0.35 meters, right? The force isn't 10.5 now. We don't know what the force is now. But the good news is it doesn't matter because the spring hasn't changed. The displacement has, but the spring hasn't. That means the spring constant will still be 30 newtons per meter. Does that make sense? Just because we've changed how much we've stretched it doesn't mean the spring itself has changed. When we made those elastic guns as kids, we stretched the elastic further and further and further and further, the elastic was still the same elastic, and it still had the same elastic constant. It just didn't have the same force or displacement. So it's still 1/2 of 30 times x squared. X this time is 0.20. So let's figure out what that one is now. Let's say 0.5 times 30 times 0.2 squared gives me 0.6. Now it's an easy question. Now we want to find delta EP. It's the final 0.60 joules minus the initial 1.8375 joules, which gives me negative 1.2375 or negative 1.24 joules. What's the negative mean there? Didn't I tell you that energy is a scalar? There's no direction. What does the negative mean? Jacob? Right, good. It's a loss of potential energy. And that makes sense, right? It was stretched further, and then it stretched less. So it's a loss of elastic potential energy. That's it for that question. Okay, the big thing here, obviously, was this part right here, right? The 30 newtons per meter. The spring constant for that spring will never change. If you find it using data, force and X, force and displacement data, then keep it that number. Don't change it just because you have a different displacement. Try these 5 questions. 5 questions for practice problems? Goodness gracious. All right, let's see what you can do with them, and then we'll take a look at them.